Sketch r vector and the derivative of r vector at the given value of a. Then sketch the curve defined by r vector and the vectors r at a and r prime at a on the same set of axes. Let's begin by recognizing that our vector function is a function of two components. It has an x component and a y component, each of which are functions of the parameter t. The x component of our vector function is given by root t, and the y component of our vector function is given by t minus 4. Being a function of two components, let's see if we could sketch this in the xy plane. The y-axis will be vertical, the x-axis will be horizontal. To sketch it in the xy plane, can you think of a way where we could transform this vector function into an expression that we can maybe more easily handle? Let's try to express one of our dependent variables in terms of the other. For example, maybe we could express x in terms of y, or perhaps it might be easier to express y in terms of x. The reason why I'm influenced to try to express one variable in terms of the other is that I see that y is a linear function of our parameter t. Since y is a linear function of our parameter t, I could see that I can express t in terms of y. But in expressing t in terms of y, I could then express x in terms of y. X is equal to root y plus 4. And if we take the square of both sides, we get x squared is equal to y plus 4, or y is equal to a parabola given by x squared minus 4. This is something that I know how to graph. I know how to graph y as a function of x. So let's take advantage of that. This sketch, this curve, I recognize to be parabolic, where the vertex is going to be at the coordinate 0, minus 4. And I get that because the minus 4 provides a vertical downshift on the y-axis. Let's indicate that. We'll go down 4 units on the y-axis. And let's go ahead and indicate the scale on the x-axis. Let's indicate a scale on the negative x-axis. And let's also go up on the positive y-axis. Finding the y-intercept of this, we could find the y-intercept, or rather, let's find the x-intercept. To find the x-intercepts, we set y is equal to 0. That would be 0 equals x squared minus 4. Solving this for x, we get x equals plus or minus 2. I'll indicate that in my graph. X is equal to plus or minus 2. Those are our x-intercepts, and we already know that the y-intercept is going to be at 0 minus 4 because we find the y-intercept by setting x equals to 0. This leads us to y equals minus 4, which we already knew. Therefore, our sketch is a parabola centered about the y-axis with the y-intercept that is equal to minus 4. Well, let's now determine the orientation of this parametric curve. Since vector functions are vectors whose components are functions of a parameter, and in this case the parameter t, this curve has an orientation. This orientation could take us from left to right on the curve or from right to left. So to determine the orientation, let's just pick two values of t and see where it takes us. Let's try t equals 1. When we try t equals 1, we know the position vector evaluated at t equals 1 is going to be root 1 for the x component. Well, I just lost my problem up there. That might actually be beneficial because it gives me more room to work. So I'm going to move some of this work up top. There we go. That'll be a little bit nicer for us now. Well, for t equals 1, we have our position vector evaluated at t equal to 1 is equal to the square root of 1 for the x component plus 1 minus 4 for the y component. This is just 1 for the x component minus 3 for the y component. That position vector takes us to be about right here. This is the point 1 minus 3. Well, let's find another point. Let's just use t equals 0 for simplicity. R at t equals 0 is going to be equal to 0 I hat plus 0 minus 4 j hat, or it's going to be a vector given by 0 minus 4. Oh, that's just at our y-intercept. So here is 0 minus 4. Oh, and let's indicate that this corresponds to the value t equals 0, and this corresponds to the value t equals 1. So notice we are going from left to right, from the point at 0 minus 4 to the point 1 minus 3. So I will indicate that with an arrow on my curve, and this gives the orientation of our curve. Our curve is going from left to right. The problem asked us to find the position vector evaluated at t equals 2, and to find the derivative of the position vector evaluated at t equals 2. Well, the position vector evaluated at t equals 2 is equal to root 2 I hat plus 2 minus 4 j hat, which is equal to root 2 for the x component and minus 2 for the y component. Root 2 is approximately 1.7. So when we are at 1.7 approximately on the x-axis, we will be at minus 2 on the y-axis. This point right here represents t equals 2, and it is the point given by root 2 minus 2, and we could draw the position vector. There is our position vector, which I will label r vector of A. Now let's find the derivative of our position vector at that point. To find the derivative of the position vector at that point, we have to evaluate the derivative of the position vector. So this is going to be the derivative of root t for the x component, t minus 4 for the y component, and this is going to be evaluated for the value t equals 2. We could write this as the derivative of root t for the x component and the derivative of t minus 4 for the y component. And this is evaluated for t equals 2. So evaluating the derivative, for the x component, we have 1 over 2 root t. For the y component, we have 1, and this is evaluated for t equals 2. When we plug in the value of 2 for the x component, we get 1 over 2 root 2. For the y component, we get 1. Here is our answer for the derivative of the position function evaluated at t equals 2. Now we want to sketch this. So to sketch it, I am just going to recognize that this value, this derivative, is approximately equal to about 0.35 for the x component. 0.35 is approximately equal to 1/3. And so in my sketch, I am going to sketch a vector that has an x component of about 1/3 and a y component of about 1. Let's sketch this derivative vector. And to help me sketch it, I'm just going to start off by sketching it at the origin, because it'll be easy for me to find about 1/3 for an x component and 1 for a y component. For example, 1 for a y component will be along this line, and 1/3 for an x component is approximately along that line. This gives me a vector that looks something like that. That vector represents the derivative of our position vector. Well, let's see. Let's move that derivative of our position vector to the point at which we evaluated it. And that point is right there. Now, I didn't draw the best of parabolas. In fact, you could kind of see where my parabola took a little bit of a right turn. So I'm going to just fix it here a little bit to illustrate what we have. The parabola should have looked more like this. Oops, I still can't do it. Should have looked more like this. Let's take our derivative vector and move it to that spot. And notice that derivative vector is tangent to our curve, to the parabola, at that point. So what does this confirm for us? This confirms that the derivative of a vector function evaluated at a point is parallel to the tangent line of our function at that point. This tangent vector is giving us the orientation, the direction of increasing values for our vector function.